Sorry. So I take it that this talk is supposed to be about me telling you what I do, but also you getting to know who I am. And since I actually joined Drexel just last April, and I joined technically over in informatics, and then we had our wonderful new merging, and then I moved over to computing. So many of you may not have any clue who it is I am, but looking for most people, maybe. But anyway, so I am looking for new PhD students because I arrived just last April. So if this sounds at all interesting, let me know. Life before Drexel, I was a research fellow at in Edinburgh, Scotland for about 7 years. And before that, for 9 years, I was a principal research scientist at Honeywell Labs, their corporate R&D facility. And before that, I was a postdoc at the University of British Columbia for 3 years. And then I was in Philadelphia, so kind of things come back around. But probably what you should take away from that history is I like to travel, I like socialized medicine, I like whiskey. My research is very applied. Well, I like it when it's applied. I think we learn an awful lot from real-world problems and real-world applications. And so I think some of the most interesting stuff you can do comes from looking at a theoretical problem, but then taking the application portion of it very seriously. My general research area really is artificial intelligence in general, but specifically I'm kind of interested in this integration of plan recognition and planning within a single unified framework. And the funny part about this, if you talk to my theory professors from college and grad school, is that I was not a theory guy at all. And so formal models of grammar, they would have told you would be the least likely thing for me to ever think about using. So it's kind of a surprise to them, I'm sure. But then taking that general research area, it's been applied in a number of different areas. Security, because it's trivially easy to get, well, not trivially easy, it's very easy to get money to do research work. Why? It's a crucial problem that we need solutions to, so that's not a surprise. Human, robot, and computer interaction I'm very interested in because I think the real progress isn't going to get made there until our machines understand us better than we understand them. We did some work, I did some work for assistive systems for the elderly, which I felt really good about because my grandmother was getting older when I was at Honeywell, and that was another very real problem, it turns out, socially and societally. And I just started doing some educational work, which I'll talk about at the end, that I think is really, really interesting on inferring what students are doing using online games and online teaching tools. So my research motivations really started way back when I took AI 101. And the very first day of class, my professor stood up and said, I know you all thought you were doing AI and how cool it was going to be. It turns out AI is all just search. So if you don't like search, you give it up now and go home. And I was very disappointed by that. But the funny part about it is that while it's true, it doesn't tell us a lot, right? It just doesn't tell us what the search space might look like, and it doesn't, and what that search space looks like obviously has a huge impact on the speed of the solution and our ability to learn solutions and how to build new solutions. And these are obviously absolutely critical things. Then I went on for a good deal longer in graduate work and other places, and I noticed that a whole bunch of problems actually have paired problems that are going on. One of recognition of a sequence or recognition of a thing, and one of generating that thing. You see this in natural language, right? There's parsing of text that you get, but you also want to generate text, right? We want to have our systems be able to speak back to us or at least write us text messages and tweets. Reasoning about action has this in spades, as I'll talk about a lot. Even vision, it turns out, has this. If you think about some of the algorithms for vision, some of the algorithms for graphics rendering turn out to be actually very relevant for vision. So I thought that was really very interesting. Somehow or another that struck a very real chord for me. And then relatively, well, a little while ago I saw some interesting results coming out of psychology. I'm not a psychologist or even a cognitive scientist by any stretch. But they've shown that the areas of the brain that are involved in recognizing the actions of others and planning to execute those same actions, in fact, are the same. If you do MRI studies, you can show that people actually, the exact same areas of the brain light up when people watch someone else doing something and they plan to do it themselves. And for me, when you combine all these things together, what you really get out is that the same search space is being used for both these paired recognition and generation problems, and that if we don't take information about both of those problems seriously at the same time, we're losing out. We're not getting all the information or all the hints that we might about how to go about solving these ideas, or solving these problems, excuse me. I also had a mentor early on who strongly advised to steal good ideas whenever you found them, that you know, there's no point in reinventing everything, and whenever you see a really good idea, you should take it with you and do something with it. So in the people that I've known who worked in robotics, they kind of introduced me to this grounded, embodied sort of idea about how things ought to be. And they're very, very committed to this idea that all actions in the world should be grounded in execution and sensors in the real world. And I think one of the fundamental mistakes that some of the early AI work has made is that we thought we could distance ourselves from the real world. The robots guys that I know at least are very, very committed to this mirror neuron idea, and that recognizing actions and performing the same action are very, very, very related. And that if you don't have the same model, you're just being silly. I spent, you know, I told you I did my graduate work at Penn, and when you do your, well, back then at least, when you did your graduate work at Penn, they had the largest natural language processing group in the world. And so it was impossible not to hang out with linguists and computational linguists, and so you get to hear about their ideas. And I think one of the most powerful ideas that they came up with was this distinction between syntax and semantics. That what a word means is different in kind than the constraints you have on how you combine it with things. They aren't the same, you need both of them. And again, I think when it comes to planning and plan recognition, we failed there. We work in I think most planning work works in a semantic space. I know what an action does, and now I'm going to search furiously, trying to project just on the basis of effectively the semantics of an action, what's going on. And that I think is just silly. There is syntax to these things. There are patterns that we use and constraints we want to enforce in sequences of action. And finally, that again, this mirroring this same idea that the knowledge needed for parsing sentences and generating sentences is very similar, if not identical, to what you need. Well, if not, both the problems are there. There you go. So, my research program for the last, well, at least 15 to 16 years has really been this idea that I'm interested in building a system that does both plan recognition and planning, that synthesizes these good ideas that I've stolen from other places, but doesn't really suffer from some of the assumptions that the existing systems have. What that means is that it needs to use the same representation for both tasks, it needs to separate syntax and semantics of actions, and it needs to ground these actions in execution and sense states of the world. Then I started my work really my graduate work was in planning, and then I moved away from that, and I came back to it in plan recognition, because the natural language processing people had studied a number of grammar formalisms that were very powerful, and there was already kind of a school of thought that suggested that you could view plan recognition as a parsing problem. And so I thought, oh, this is a very interesting line of work to kind of follow, and that's where I got started in this sort of program. So the rest of the talk is almost except the last slide, is really all about plan recognition from here on out. And I'll come back and wrap you back in with the plan recognition. But it's important or worthwhile at least to try and understand the difference between plan recognition and activity or behavior recognition, which is very, very popular right now. Activity or behavior recognition really is the labeling of real-world sensor data with activities or behaviors. I have a sequence of video images, and I want to say, during this window of this video image, this thing is happening. It focuses really, from my perspective, and other people's views may differ, but really focuses on correlating noisy data over time and producing a single non-structured label to that, that window of time, if you will. And there's been some really outstandingly successful algorithms based around hidden Markov models, conditional random fields, a whole bunch of different things. And that's great. Plan recognition, on the other hand, is kind of one step up from this. Plan recognition is the identification of the plans that are being carried out by the agent, given observations of their actions, and a library of plans to be recognized. And it focuses on these structured representations, not a single label, but rather a structured representation, a tree, some kind of complex control structure, but something much more than a single label. You're talking about focusing on combining multiple partially ordered actions into plans for higher level goals. And most of the successful algorithms for this have been based on logic and hierarchy rather than kind of the continuous probabilistic approaches that we've seen for the activity and behavior recognition work. I definitely fall within the plan recognition work, though I'm interested in using probabilistic grammars. And so I think it kind of crosses these two things very nicely. But one of the key ideas is this, and I've already kind of alluded to this, way back in 1990, Mark Verlaine suggested talking about plan recognition as parsing. If you've ever seen a natural language parser, they output hierarchical structures. They build these very nice structures that you can project things from. You can say, oh, I've seen the noun phrase. I'm now probably, I'm in English, I'm probably looking for a verb phrase at this point. And suggested this. I'm shocked and stunned and appalled that this idea wasn't taken up more in the community. There are about 4 or 5 papers back in the early 90s, and then silence, deafening silence for about 15 years. But the idea basically is that grammars, these grammars that we have, define the acceptable plans that you can be recognizing. Your plan library is defined in terms of a grammar, and for those people who have studied formal grammars, either in theory or a natural language processing class, they're in luck. They've already got the tools that they need to do some kinds of plan recognition. How many people are good formal language people? I don't have to talk very much about it. Nobody. Excellent. Great. There you go. I can say anything I want now. One of the latest things is the move in natural language processing has been a move away from kind of traditional context-free grammars that you might be used to seeing to what they call lexicalized grammars. And I'll show you an example of this. But one of the better known ones was formalized by Mark Steedman, actually well before 2001, but the standard text on it that everyone cites is out of 2001. And the real idea here is that normal grammars, I'm going to have to move faster, normal grammars conflate all of the domain-specific information that you might have in the methods and the rules for the grammar. And the idea behind lexicalized grammars is you want to separate that. You want to separate out all the domain knowledge into categories, and you want to use domain-independent information in the combinators to combine them. For those of you who remember your Greibach normal form, this has a single terminal symbol followed by non-terminals. It's a generalization of that. And they're incredibly powerful. They're not incredibly powerful. They're very powerful, and the really interesting things about certain lexicalized grammars, and CCGs in particular, is that they actually fall in between the normal context-free grammars and the context-sensitive grammars. So they're more expressive than context-free, but strictly less expressive than context-sensitive, and they have very fast runtimes. This seems like a really great idea to me. I'm very excited. I'm like, look, I'm going to have fast runtimes for my grammar. This is great. So if you want to build a category in CCGs, they're basically functions. You want to think of this as a functional type. And they're defined recursively in terms of basic categories, which is just a set of your terminals that you want to talk about. And then you can build complex categories as the atomic categories. You build complex categories with these funny slash operators. And the slash operators tell you, they separate the result of the category, which is on the left. Yes?
I'm familiar with the word category in a sense that has a bunch of structure with it. Is that the sense, or is it just...
You mean like
category?
Logical structure?
Yeah, there are categories in category theory.
Right. So this is related to those.
Okay.
It's a different syntax for them, and we'd have to talk offline a lot about how that works. But for now, just bear with me as a piece of syntax. We have this slash operator, and the slash operator actually separates the result of the function on the left-hand side from the arguments that it requires on the right-hand side. So this is a functional category that's going to produce a z, given that you see a w, an x, and a y before it. That's the leftward looking, right? And the rightward looking, it's a category that's going to produce a z if you see w, x, y, whatever afterwards. And then we just have these completely domain-independent combinators that we can actually use to put our functions together. And we have rightward application, leftward application, exactly what you expect them to be in terms of application and composition, which again, you're taking two functions and composing them. This just formalizes your intuitions about how that works. So here's an example plan lexicon for a cell phone domain. If you wanted to talk on a cell phone, you have two different plans here. One is for reporting a fire, one is for chatting. And we have a number of different actions that we can have. We have dialing on a cell phone, talking on a cell phone, getting the cell phone, opening the cell phone. It's a flip phone. It's one of those old ones. And if you see these things in this order, we can actually use, we assign the categories associated with each one of these actions. And we're going to have to do a little bit of search, but not very much. We assign G to get, because that's what get has as its type in the lexicon, or its category in the lexicon. Then we have open, and it has category O. And then when we see dial, it's got this complex category, and we're going to use backward application to remove the O argument. And then we're going to see G, and we're going to use backward application again to remove G. And then we use forward application to combine it with talk, and we wind up with a plan, recognizing a plan for chatting. So life is good. We've parsed that sequence of observations. We've produced a plan, or we've recognized a plan for chatting. Here's the very quick one-slide probability model point. If people want to talk about the probability model, we can do that offline. The basic way that the algorithm, the plan recognizer works is to do weighted model counting. You compute the set of all the explanations that you could have, or all the parses for the set of observations that you get. Yes, that is a big space, but we have ways of controlling it. And then you just, you divide the probability mass associated with those plans you care about, i.e. the ones that have some goal that you're interested in, by the probability mass of all the explanations that you have. Here's the method that you use for actually computing the probability of a given explanation. And that just has two terms. One is a very standard term from the natural language parsing literature. That is the probability that the category is given the observation that you have. And then the other one is the sum of the probability of the plans that you have having being the plans that are actually there. This is fundamentally committed to having multiple plans going on at the same time. So you want to actually have a term that allows you to say, oh, what's the probability that I'm doing these 5 things at the same time? And that's what that term actually captures for you. So that's, like I said, that's the one slide on the probability model. I haven't told you everything you need to know about this, but that's what you're going to get about the technical parts of the algorithm. We have some very nice technical results that come out of this plan recognizer. It does handle, it easily handles context-free grammars, which makes it more expressive than, say, your hidden Markov models or other kinds of models. So that's a good thing. You can recognize plans that are A to the n, B to the n. And if you think that doesn't occur, just think about shipping. Every time you put something in a truck, it has to come back out. bad when packages stay in the trunk. Partially ordered plans we can handle trivially without significant computational explosion. And that's a very nice result. It handles multiple concurrent interleaved plans, so you're doing 4 different things at the same time. This is a significant limitation of most prior work on plan recognition, and the fact of the matter is humans do multiple things at the same time, and you need to be able to recognize that. It's particularly appropriate in security domains where there's lots of things going on at once. And it handles, we have an efficient method of representing and reasoning about plans with loops, so that's kind of nice. The question everybody would ask at this point is runtime. You know, does it work fast or not? Well, that kind of depends. And what it kind of depends on is the grammar that you have. This lovely graph over here, it was explained to me that DARPA program managers always like graphs that go up and to the right. So this one goes up and to the right, but I really would have reversed it if it was me. What this is showing you is that you can drive the runtime of the system basically, well, to very, very acceptable levels. This is seconds on the right, so you're looking at tenths and hundredths of seconds for these, as long as you delay or are willing to delay the recognition of some of your plans. So if you can separate your plans into those plans that you need an immediate recognition of, and those that you're willing to wait to recognize until after the plan's completed, you can actually drive the recognition time down very low. We also have had some really nice luck parallelizing the algorithm, so that the graph on the other side shows you that we're getting basically a linear speed up using work stealing as a method of allocating work to threads. So this is also an algorithm that you can basically farm out to as many processors as you want, and that just gives you a nice linear speed up in how fast everything runs. So that's also a nice little piece of work. So some applications, because Spiros needs to leave in 5 minutes. Like I said, computer network security, this is one project that I'm working on right now. This is funded by DARPA. It turns out that if you have cloud-based computing, the real problem from a security standpoint of cloud-based computing is that it has a homogeneous architecture to it, which means if one of your servers is subject to a particular attack, then all of them are. And that's a very bad thing. So this project is specifically focused on building systems that will actually kind of proactively recognize what an attacker is doing and attempt to try and take action to prevent them from owning your entire cloud. And you'll see probabilistic attack plan recognition sitting right in the middle of the architecture right there. Very nice. If you're interested in more about this, you can ask me about skeptical systems, and I'll be happy to tell you about it. Another application, I'm working with some people in Europe. There's an EU FP7 project to build cognitive humanoid robots, and that's the robot. He lives in Karlsruhe. And how does plan recognition fit into this? Well, if you want to actually be able to learn new plans, you have to actually be able to recognize what you already know in order to learn these new things. And if you really want to understand more about this, ask me about potato peelers, and I have a whole story about potato peelers. The third application that I'm really interested in right now is teaching students. It's not funded yet, but I just got started working with a great guy by the name of Kobe Gall at Ben Gurion, and he has a number of applications, a number of different software applications for education. One's a Bayesian net, or a Bayesian reasoner teaching tool, and one's a chemistry teaching tool. And the problem really is that the kids love playing with these things, but you need to actually be able to recognize what you'd like the system to do is to recognize what the students are doing and when they're learning the right things and when they're not learning the right things, and flag down the professor or the teacher and say, hey, this kid has learned the thing we know he's done, or he hasn't learned. Clearly he's never actually managed to execute this plan correctly. And what can we do to kind of aid in that process? I've actually done a bunch of work in the past on assisted care for the elderly. As I said, that was work that happened out of Honeywell. It was really great. I'm happy to talk about that if people want. Insider threat, this is incredibly interesting stuff. One of the things, again, I did back at Honeywell was worrying about document misuse and people being able to, they're authorized insiders, but how do you recognize when somebody's actually misusing the authority that they have? And finally, we did some work on assistive systems for large-scale manufacturing and oil refineries. Okay, that was the application. Here's my one final slide. This is the teaser for plan generation. So I have built a planner that actually uses exactly the same CCG grammars. It's very similar to hierarchical task network planners, but with a few key differences. Whereas normal HTN planner would kind of have a single method that you could think of as a single production in a grammar. This actually looks at the CCGs. The key thing to think about it is that they're actually looking basically at a tree spine. So when you assign a category to a given observation, you're actually defining a tree spine. And what that means is that your planner is working with a set of trees rather than a set of single expansions. So critically, the CCG actually provides very interesting information about how to build the plan. That is the order of the steps you want to take in building the plan. Not simply what are the substeps of the plan, but the order in which you're supposed to go about building this plan. That's actually critical information, right? What we care about is building plans faster. If we don't have information about how to build the plans quickly or how to build the plans effectively, I just have knowledge about how sometimes this works, we're actually we're not keeping the right information in our plan structures. Also, it has the property that CCG-based planning requires that each planning step actually add a basic action. So you're going to add this locomote to shelf every single time you kind of do a planning step, unlike HTNs that kind of expand out to this level and then try and build a whole plan and then want to expand each one of those and build a whole plan at that level and then want to expand all the before they get down to basic actions. Because the CCGs are lexicalized, if you drive it out of there, you have to add a basic action every single time you're doing an operation. And then, most interestingly, I think, it actually enables a very serious kind of divide and conquer in the planning space. Notice that this category actually has things that have to happen after it and things that have to happen before it, which means when you put this on the timeline for your planner and you say, I'm going to do that action, it makes a commitment about what's happening then, but it also tells you what you can do before or what you can do after, and you can actually do a sort of divide and conquer as you're going, which allows you to move away from strictly back chaining from the goal or strict forward progression from the initial state. There you go, and that's it. I don't have a thank you slide. I should have a thank you slide, but I don't. There's no. There you go. Oh, and Spiros already left. There you go. Yeah.
So you said your grammars can recognize plans with loops. So
yes.
What kind of constraints do you have on loops? I'm assuming you cannot recognize any kind of loops, right? That would be possible.
So the major constraint for the efficient, it's a context-free grammar, so we can recognize inefficiently anything you can recognize in a context-free grammar, and that includes lots of kinds of loops. Some of them are wildly inefficient. Anything that's left recursive, you don't want to go anywhere near because it actually won't terminate. So what you want to do is, we can rewrite that as a right recursive grammar, so it's not a problem. That part's not a problem. What becomes a problem is if you do it in a right recursive fashion, you can sometimes get a very large number of hypotheses and about what's happening, because you're getting these partial fragments of the loop. You get each iteration of the loop, and then you get groups of iterations of the loop, and that's wildly inefficient. So what we actually do, when I say it recognizes loops efficiently, there's actually a methodology where if you have something that you can identify as the head of the loop, something that's distinctive about the beginning of it, and something that's distinctive about the end of it, you can actually code those up so that they bookend, and thereby force all of the looping activity to happen within a single category. And then you just get two explanations, and it goes lightning fast. Now, I'm not sure if that answers the question that you want, or whether you want to ask another question about it.
Yeah, just to make sure I understand. So then what you're saying is that, so you create the grammar in a way, you author it in a way that you detect, you have explicitly represented the beginning and the end.
Right.
So what you can efficiently do is recognize it
Right.
So I misunderstood. I thought you would recognize in the loop to create the grammar for the loop, but that's
No,
what
no,
I
no,
thought it
no,
was.
no, 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 no.
Okay.
So learning the grammars is another thing. That's part of what we're doing for the, or we're trying to do for the EU project. And that, well, let me say two things about that. One, the natural language people have been working on on learning CCG grammars, and they do some very, very interesting work. It's straight corpus based, the kinds of things you would expect from learning a kind of a Bayesian grammar. They win because they get lucky in the sense that natural language has the set of terminals, or the set of non-terminals that you care about really in most languages is closed class, because you know I'm either looking for a noun phrase, or I'm looking for a verb phrase, or I'm looking for a determiner, or a, and that set of things is fixed. That's not clear here at all, right? It's just not clear what the set of closed things would be. So this, I think, is a strictly harder problem in that sense. I have some ideas about how to do it, but I'm not sure. One of the things that I think is most promising for learning these grammars right now is based on an idea taken from chart parsing, wherein, can I scribble on a board? Is there a board I can scribble on? If you know, suppose you know that you have, I have a parse that has an A and a B here, and I have some action that I don't know in here, right? But I have examples from this before that resulted in G, right? Well, what I can do is I can immediately infer, because I only have these three things, that the category of this action really has to be basically a G looking to its left for a B and looking to its right for an A, right? That I can construct that by looking at it. I know if someone tells me this is a plan for G, and I've seen the whole plan and I have a terminator for it, there's the category. It's got to be that. There's no other real option. So you don't need to do complicated. Well, you can read the category for that thing off. Obviously, there's some more complex issues that come along if you've seen a category for it, but you might want to change it, or A and B don't necessarily have single categories. Any number of things that can come along and cause you trouble there. But there's been some really good evidence, or really, really nice work out of Washington and Edinburgh, and now Washington because the guy moved, about doing exactly that kind of inference in language settings. And so we think that, well, at least I think, that we can probably take some of that and directly apply that to the kinds of domains that we're looking at here for learning these grammars. But obviously learning grammars is something that the natural language people haven't solved either. So if they have an answer, we would just use their answer wholesale. But I'm also very interested in it's the potato peeler story. So I'll stop the answer there. And if somebody wants to know about potato peelers, I'll explain potato peelers. But other than that,
Thanks.
eat food. Yes.
I was wondering, we had like assemblers, right? And then we had like formerly translators for like Fortran and MAD.
Yes.
And then compilers like C++, Pascal, and now they got these interpreters for high-level languages like Perl and Ruby.
Right.
Is this like the next step to try to get us closer to natural language, computer
So
language?
I think there's some interesting ideas about trying to put these kinds of grammars and action kinds of grammars together with actual natural language. I haven't gone there yet, but I think you could. I think there's some very interesting overlap between those, and it's one of the reasons that I'm very interested in using formal grammars, is because I think those things, there's also some good cognitive evidence that kids learn to plan at the same age that their language skills skyrocket. There's a really interesting developmental phase they go through that also gives you some evidence that maybe the kinds of formal grammars in the search spaces that we're talking about for action and language ought to be very, very similar. So that gives us some reason to think that those things might be related. I haven't gone anywhere near that yet, but could be.
I just want to say if we start to see some of this stuff starting to appear in the next generation computer language.
I don't know. I have never talked with anybody about it, but I think it'd be an interesting idea. Yeah?
So I'm sorry I got a little late, but
That's okay.
You were talking about those lexicalized context-free grammars.
Yes.
And then you talked about the probabilistic model
Yes.
of the plan. In natural language processing, I've seen maybe that they are moving towards using lexicalized probabilistic context-free grammars.
Yes. Well, that's what these are.
So the grammars themselves are probabilistic already?
Oh yes. Oh yes. 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 So oh, sorry. Let me go back. Oh, right there. So you have two probabilities that are associated with every single one of these productions, or every single one of the categories. There's a probability that the category that the observation is, the category is assigned to it given the observation. This is completely standard in natural language processing. This is exactly the probability of the use of the production in a context-free grammar. It's generalized for a lexicalized grammar because you actually condition on the terminal that you're using. This is the step that's not present in natural language processing. And the reason it's not present in natural language processing is you only ever have one sentence at a time, right? You would never process two interleaved sentences. It'd be like me saying two sentences at the same time in an interleaved way. You'd never understand what I was saying. We don't do it. Nobody does it in any language.
But aren't you waving your hands while you're saying that? So there are two channels of communication.
Right, that's true, and all the people that I know who worry about this actually annotate these grammars, so the category then carries along things like my hand waving and the intonation curve that I would actually include. You can actually mark all of these categories with extra, what the natural language people call features, that include secondary things like my hand gestures, how excited I get, all kinds of things. One of the things that is particularly interesting about CCGs is that you can get what are considered non-standard constituents in the language. And sometimes non-standard constituents have interesting intonation properties, which is one of the reasons that some of the language people love them or are very excited about them. Anyway, back to the second term of the probability model. Because you only ever have one sentence at a time, you never see this. But we're interested in multiple plans happening at a time, and so we actually have to be able to capture the probability that you would be doing your laundry and making a grilled cheese sandwich and vacuuming, I don't know, all at the same time in your house, which you might be doing, right? Or you're grading and reading email and twittering all at the same time. And those things all have separate steps, and you want those plans to be all considered separately, so you need terms for that. Because you would like to bias simpler explanations. What you want to be able to say is, yeah, if you really do have multiple plans going on, then that's great. If not, I'd rather you biased it towards simple explanations, and so you have a term there that does that. The K is just a normalized. So yes, but we have both those pieces of information. I didn't even tell you there's actually a state model that goes along with this, and that's probabilistic too. So you can do state projection in your planning. So you can say, oh, I'm in this state and I see this action. Here's the state I most likely wind up in, and there's a probability model for that as well. So.
What do we do when we have lots of sensors of various kinds, and so we're observing what an agent is doing, but I guess we need to learn or discern which of those sensors are relevant to recognizing a plan.
Right. So there are two questions there I think you're asking. One is, how do I learn a good model for a cluster of sensors to say these sensors are all reporting the same thing at the same time? I haven't really looked at that with this technology at all. I think that's a problem that is best addressed by things like HMMs or Bayes nets or just standard, much more standard, what I characterize as activity recognition. And for almost all the applications that I've worked on, we've had an activity recognizer that was there that reads through the audit logs or reads through the sensor logs and says, oh, you had, in the case of computer network security, you had 5,000 pings. Well, that's one event. That's not 5,000 events. That's one, right? You had 1 million requests for X, whatever, and they were identical. Well, it's probably a single flooding attack. That's probably not 5,000 different requests for the same thing. Though apparently Ellen DeGeneres crashed Twitter last night by tweeting at the Oscars, so you never know. That's It could be. Anyway, so that's one problem, right? And that's not a problem that I've done a lot of work with at all. The learning how those things correlate into a grammar comes back to, I think, learning the grammar question. So I think there are two different things there, and there's a really insidious problem that has to do with making sure that your low-level models actually coherently line up, because you can imagine multiple interpretations from the low level that overlap. And when that happens, some very bad things can happen, because you get half an explanation from one area and half an explanation from the other, and they don't line up, and then you don't get a whole sentence for either one, and bad things happen.
So I see and hear, but something doesn't line up.
It's more like you see the first 3/3 of one sentence and the last 3/3 of another sentence. and you can't tell which sentence was right, because it turned out there was a lower probability but better explanation that was the whole first sentence and a different second sentence. It's that much more. It's an intuition.
Take a food break now and then ask questions.
Yes, food break. Food break. People eat food.